Hello and welcome to this video on indices. We're going to start with a refresher of things that you met at GCSE. So for example, if you were asked to write the square root of x in index form, you should remember that that means it's x to the power of a half. The fifth root of x would be x to the power of a fifth. The cube root of x would be x to the power of a third. The fourth root of x would be x to the power of a quarter, and so on. This expression is the same as e squared to the power of a third, and then we can times the 2 and a third together to give us a final answer of e to the power of 2/3. So the 2 on top represents the squaring, the 3 on the bottom represents the cube rooting. If you have a variable on the denominator, then that tells you that you'll have a negative index. In this case, it's m to the power of -1. Because u is squared here, and on the denominator, that means that it will be u to the power of -2, but we're also timesing by 4, so the final answer is 4u to the -2. W root w is the same as multiplying w to the power 1 by w to the power half, so that's w to the power 1.5, but we would encourage you to write that as w to the power 3/2 using an improper fraction. This expression simplifies to x cubed over x to the half, and when we're dividing terms with indices with the same base, we subtract. 3 take away a half is 2.5, or 5/2. So with an improper fraction, the final answer would be x to the power of 5/2. Now we're going to look at the values of some terms where 4 is the base number to various indices. Half, as we know, as an index, represents square root, and the square root of 4 is 2. Here the 3 on the top means cubing, the 2 on the denominator means square rooting. So 4 cubed is 64, 64 square rooted is 8. Or you could square root 4 first and get 2, and 2 cubed is 8. Alternatively, you could rewrite the 3/2 as 1 plus a half, and that would give us 4 to the 1 times 4 to the half, which is 4 times 2, which again is 8. The negative index tells us we've got a reciprocal, so in this case it's just 1 over 4 to the power 1, which is a quarter. Whereas 4 to the power of -2 is 1 over 4 squared, which in turn is 1/16. 4 to the power half is 2, because it's the square root of 4, so 4 to the power of -1/2 is 1/2, or just a half. Anything to the power of 0 is equal to 1, so hence 4 to the 0 itself is equal to 1. 4 to the power 1.5 is the same as 4 to the power 3/2, which we've already established is 8. But again, you could do this by doing 4 to the 1 times 4 to the half, adding your indices together, and 4 times 2 is again, of course, 8. This slide contains reminders of what we've been talking about, so important things to remember in terms of indices in relation to the fractions and the negatives, and then the 3 rules in terms of multiplying, dividing, and powers and how they can be used, each with an example. Underneath that, we have some questions. I'm going to attempt question 2b on the next slide. If you could pause the video and try some of the other questions, or maybe watch the slide with 2b and then come back, that would be great. So question 2b asks us to solve the equation 5 to the power x plus 3 is equal to 25 to the power x minus 2. Now, in order to do that, it would be really helpful if we had the same bases, and 5 and 25, of course, are not the same number, but conveniently 25 is equal to 5 squared. So if we replace 25 with 5 squared, we have 5 to the power x plus 3 and 5 to the power of 2 lots of x minus 2, which in turn implies that x plus 3 must be the same as 2 lots of x minus 2. If you expand the bracket, so you get x plus 3 is equal to 2x minus 4, and then if you take away an x and add the 4, you get a final answer of x equals 7. If you want to go back and check it, you can substitute 7 back into the original equation. That would give you 5 to the power of 10 and 25 to the power of 5. And since one index is half of the other one, and the right way around, that does actually work out. Please pause the video for some other index questions to have a go at. Answers will appear in a different slides. Here's another equation to solve with different bases. Again, answers in the different slides. And finally, I'm going to show you how to solve a pair of simultaneous equations using the index ideas, and there'll be 2 more to try on the final slide. So we have 5 to the power of p plus q is equal to 125, and 6 to the power of 3p plus 2q is equal to 36. And again, we've got the issue that it'd be nice if we had the same base numbers on both sides. So in my first white box over on the left, I've rewritten 125 as 5 cubed and 36 as 6 squared. So now each of the equations has the same base numbers. And that implies, therefore, from the top equation that p plus q is equal to 3, and then from the other equation that 3p plus 2q is equal to 2. This, as it says, is a pair of simultaneous equations, but neither of the coefficients of p nor q are the same. But if you say double the first equation to get 2p plus 2q equals 6, then now both of the q terms have a coefficient of 2, and we can just subtract. 3p take 2p is p, but 2 take away 6 is negative 4, so the value of p is negative 4. Substituting that back into any of the equations, but p plus q equals 3 is the simplest, gives us negative 4 plus q is 3, from which q is 7. And again, you could go back and check your answers. And then to finish off, we have 2 more pairs of simultaneous equations. Same idea again. Answers will be revealed in a different slide. Thank you very much for listening.